This week we will work with three special types of functions that will appear throughout the course: quadratic functions, polynomials, and rational functions. Quadratic functions are typically represented by parabolas, so that is curves that go up and down, or down and then up, and they appear in many practical situations. So one example of a situation where this type of functions will appear: imagine that you own a movie theater and you want to see how much revenue you will get by increasing the price of the tickets. It's clear that the revenue cannot go forever, so you cannot price your tickets at any value you want, because the amount of people that will come to the movie theater will decrease as the price of the ticket increases. So what you will typically have is a situation like that you increase your revenue as you increase the number of, as you increase the amount that each person should pay you for entrance. Yeah, so the price of the ticket, you go up, your revenue goes up, but then it reaches a point after which, if you increase more the price of the ticket, then the revenue goes down. Yeah, so it has this peak and down behavior that is described by a quadratic function that will give you this shape. Yeah? So we'll look at some properties of quadratic functions now, not in the context of applications at this point, but just to introduce some theoretical properties that they have, and then later we will see how they will work in applications. As you might remember from previous math courses, quadratic functions are described by expressions of the form a times x squared plus bx plus c. They are called quadratic because of the exponent 2 on the x, and that's the main characteristic. The highest value of the exponent in x is going to be 2. And we will be interested in two properties of this function: the vertical intercept and the horizontal intercept. The vertical intercept is the point where the graph of a quadratic function, a parabola, will touch the vertical axis. In this case, it's represented here by this circle. Whereas the horizontal intercept, which will often in the case of parabolas be 2, are the values here where the graph touches the horizontal axis. These values correspond to something that is also called the solution, or the zeros of the function, and this can be obtained by a general formula that probably you will remember. For a quadratic function in general form, f of x equals a times x squared plus bx plus c, the vertical intercept is found just taking the value of x equal to 0, which, if the function is itself in general form, that means that f of 0 will be only the coefficient c, because the parts with a, x squared, and bx will cancel out. To find the horizontal intercept, we need to make the function itself equal to 0, and then find the corresponding values of x that will make that happen. So we have f of x should be 0, so that means that a times x squared plus bx plus c is 0. And this might be a little bit hard sometimes to solve, but we are very lucky because for quadratic functions there is a method that will always work. For a quadratic equation in general form, to find the horizontal intercept, or the root, or the 0, or the solution, all these names mean exactly the same thing. We can use the following formula. The values of x that will satisfy this relationship f of x equal to 0 are found by calculating the quantity here shown in this nice blue rectangle using the coefficients a, b, and c. We can consider a more general type of functions than quadratic by expanding the number of coefficients that we can have and the different powers of x that can appear. So in general, a polynomial is a relationship of the form f of x equals a0 plus a1x plus a2x squared plus a3x cubed plus etc. until any degree we want, xn. And actually that's the first concept. The degree of a polynomial is the highest value of x that appears. The numbers multiplying the powers of x, a0, a1, a2, and so on, are called coefficients. The leading coefficient is the coefficient of the highest power of x that appears. In this case, that will be an. The leading term is therefore an times xn, the term that has the degree of the polynomial plus together with the leading coefficient. And the intercept, or also the independent term, is the coefficient a0 that doesn't have powers of x next to it. For polynomials, we will be interested also in vertical and horizontal intercepts, as in the case of quadratic functions, although there are no general formulas for polynomials from degree 5 and above, and the formulas for degree 3 and 4 are not really nice, not really useful either, so we're not gonna touch on those. Our final example of functions are rational functions that consist of the quotient or the fraction of two polynomials. In this case, one polynomial of degree m and one polynomial of degree n. For rational functions, we will be interested in similar properties: the vertical intersect, the horizontal intersect. So in this case, the vertical intersect will be again when evaluating the function in the value x equal to 0. The horizontal intercept will be when evaluating the numerator of the fraction, in this case, to 0, and as long as the denominator is not 0 itself, so otherwise we will have a division by 0. And there's another additional property that we will consider for rational functions, which is asymptotes. Rational functions have vertical and horizontal asymptotes. A vertical asymptote is a vertical line to which the rational function will approach but never touch and never cross. And an horizontal asymptote is a line that the rational function will touch but will also never cross, and will always get arbitrarily close to either a vertical or an horizontal asymptote, but never touch. To calculate vertical asymptotes, we will need to make the numerator, so that's the upper part of the fraction, equal to 0, and make sure at the same time that the denominator is not equal to 0. To find the horizontal asymptotes of a rational function, we'll have three possibilities depending on whether each of the conditions is fulfilled. When the degree of the denominator m is bigger than the degree of the numerator n, then there is a horizontal asymptote at y equals to 0. Where m is smaller than n, there are no horizontal asymptotes, and when m and n are equal, then the horizontal asymptotes is the ratio between the leading coefficients an and bm, or in that case will actually be an divided by ebn, right? Because m and n will be the same.